Alright, the topic today is topic 4, materials. We will start with fluids. A fluid is a material that can flow. Liquids and gases are fluids because they can flow. Solids, if it can flow, is a fluid. For example, sand. Sand can flow, so sand is a fluid even though it's a solid. But when we talk about fluids, it's mostly liquids and gases that we talk about because those are the ones that can flow. Alright, let's start. Okay, so if we have fluids, density and upthrust, you should know the equation for density. Density is equal to mass over volume. This equation is very important. Rho stands for density, it's a Greek letter. Then simple M for mass, capital V for volume. You have to remember this equation and the definition. Okay, so when you write the equation in words, it actually gives you the definition of density. Density is a measure of the mass per unit volume of a substance. A fluid is defined as any substance that can flow. And also whatever is in bold black letters is important here. You should know the meanings, the definitions of those words. Okay, let's see now. You can see here we have rigiform or styrofoam, and it is very having a very low density. So even though it has a huge volume, even a small person can lift it. Density is equal to mass over volume. So even though the volume is very large, its density is very low. This material here. Okay, so we have an example. A house brick is 23 centimeters long, 10 centimeters wide and 7 centimeters high. Its mass is 3.38 kilograms. What is the brick's density? Very simple again. You are directly given the mass, but you are not given the volume. So that means you have to find the volume. And this is a brick. A brick is a cuboid. It's a rectangular block. You can then find the volume of the brick by multiplying the length into width into height. So here we have 0.223. They convert it to cubic meters and they give the density in kilograms per cubic meter. This is the SI unit. You can also give the density in grams per cubic centimeter, but this it depends on how big or how small the density is. If you want to convert from grams per cubic centimeter to kilograms per cubic meter, you multiply by 1000. Right, so here they calculate the volume in cubic meters. The mass is given, so we use this formula and substitute those values into the formula, and then we get this. And then the density of the brick is 2100 kilograms per cubic meter. And if you want to convert this to grams per cubic centimeter, you divide by 1000. So it will be 2.1 grams per cubic centimeter. Next example. At 20 degrees Celsius, a child's balloon filled with helium is a sphere with a radius of 20 centimeters. The mass of helium in the balloon is 6 grams. What is the density of helium at this temperature? To do this question, you have to know the formula for volume of a sphere. You have to know this formula, okay? I don't think you will get it in your formula sheet. The volume of a sphere, the surface of area of a sphere, both of those equations are very important. You should know them. Volume of a sphere is 4/3 pi r cube. The surface area of a sphere is equal to 4 pi r squared. You can remember when we say volume, we give the unit in cubic unit. So you can see this is pi r cube. So you can remember it that way. So 4/3 times pi r cube is the formula for volume. 4 pi r squared is the surface area. Surface area is equal to 4 pi r squared, surface area of a sphere. There you can see it's a square, so r squared. So you can remember it's the formula for area. Okay, they have given us the temperature because the volume can also change with temperature. If the volume is, if the temperature is high, the volume will also be high because materials expand when the temperature increases. Okay, and you can see here it's a sphere of radius 20 centimeters. So we can find, we are given the radius, so we can find the volume using this formula for volume of a sphere. Again, the cubic, this is in cubic meter, so we have to convert this to meters. Okay, we have convert here into meters and substituted, and then you get that volume. Now density is mass over volume. The mass is here in grams, so we convert it to kilograms, and then we get the answer in kilograms per cubic meter, which is the SI unit. You can also write it in grams per cubic centimeter. So if you want to write this in grams per cubic centimeter, you need to divide it by 1000. Alright, let's go through this. Okay, learning tip: as objects expand when they get hotter, the volume depends on the temperature, and so the density must also be affected by changes in temperature. I already explained that when the temperature increases, volume increases. So when the volume increases, the density decreases. So when the temperature increases, the densities of materials decrease, because the mass is constant and the volume increases. Density is inversely proportional to volume. So when mass is constant, volume increases, density decreases. Okay. Here is a table showing densities for different materials. Okay, so we have air, pure water, sulfuric acid, cork, and you don't need to memorize this. Just for you to have an idea, they have given you this. And you can also see ice, 990 kilograms per cubic meter. Pure water, 1000 kilograms per cubic meter. And they have also given the state and the temperature, and there is an exemption for water. Water has its highest density at 4 degrees Celsius. You can see the density of ice is less than that of water, because I told you the water has its highest density at 4 degrees Celsius. So it's not like the other materials. Below 4 degrees, when the temperature decreases from 4 to 0, the density decreases. Okay, now generally what should happen is, when you go from a solid to a liquid to a gas, the density decreases. Okay, so a solid of the same material is denser than a liquid of the same material, and a gas of the same material is less dense than that same material in its liquid state. But for water there is an exemption. Okay, that's why ice floats on water. Ice is a solid, water is a liquid, but we expect the solid to have a higher density than a liquid, but in the case of water that is not the case. Okay, so you have to remember that exemption for water. Okay, then the next topic is upthrust. Again, this is very important. Upthrust is the weight of fluid displaced. Okay, you have to know that upthrust is the weight of fluid displaced, and this is known as the Archimedes principle. It turns out that the size of this force, which is upthrust, is equal to the weight of fluid that has been displaced by the object. This is known as Archimedes principle. And the upthrust is due to the pressure differences at the top surface and at the bottom surface. Now, in a liquid, pressure increases with depth. We have the formula for pressure in liquids. Pressure equals rho GH. Let me write that. You have also, I think, learned in the 9 to 1 O-level classes. We have pressure equals rho GH. Now rho is the density. Okay, so let's assume the density of this liquid is constant, and the G is the gravitational field strength. P is the pressure. Okay, so here we have charting out P. This is rho. Now what happens is, these two are constant. The rho and the G are constant, and the H is the depth from the surface of the liquid down. Okay, so that's what we call depth. Okay, so this is the depth of the, so when the depth increases, the pressure increases. Now you would have noticed that when you swim underwater, the deeper and deeper you go, the greater and greater the pressure on you. Okay, so the bottom surface is at a lower depth, at a higher depth than the top surface. So when the height or the depth increases, the pressure increases. So therefore the pressure at the bottom of an object is greater than the pressure at the top. Okay, so that is what causes upthrust. The difference in the pressures causes a difference in the force, and that results in a different that results in upthrust. So if I draw a diagram, let's say we have an object, maybe a rectangular block, and let's assume that this is underwater. Okay, so this is the rectangular block or cuboid, it is underwater, and then we have the pressure on the top surface. The pressure on the top surface will be greater than the pressure at the bottom surface. So let's say now, okay, we'll draw this one. Okay, so let's say this is underwater. Now this depth here to the bottom surface, let's call it h2. This depth here is h1. Now the areas are the same. The area of the top surface is the same as the area of the bottom surface, and we know the formula: pressure is equal to force over area. Okay, now the pressure in the liquids, now since h2 is greater than h1, the pressure at the bottom surface, okay, so I will write, okay, so we'll call this, okay, pressure at the bottom is greater than the pressure at the top. Alright, the pressure at the bottom is greater than pressure at the top. Now let's say if we apply this equation, then force at the bottom is equal to pressure at the bottom times area. The areas are the same. The area at the top and the area at the bottom are the same. So what happens is, now force at the top is equal to pressure at the top times the surface area at the top. Now if you increase the pressure, that means now, you know, since we know the pressure at the bottom is greater than the pressure at the top, now the area is the same, so that means we can say, okay, so we have pressure at the bottom greater than pressure at the top, and area is constant. Okay, area is constant, therefore the force at the bottom is greater than the force at the top. Okay, now therefore there will be a difference in the forces, so therefore we will have a resultant force. The resultant force then will be the upthrust. Okay, so because of the difference in pressures, we have a difference in the force at the top surface and at the bottom surface. Therefore the resultant force will be equal to FB minus FT, and this is equal to the upthrust. Okay, I'll call that U for upthrust. Okay, that is the upthrust. Write the full word, upthrust. Okay, now if the upthrust is equal to the weight, now you see the upthrust is due to the pressure difference. Okay, now we didn't talk anything about any other force, we only talk about upthrust here, and that is due to the force exerted by the water on the top surface and the force exerted by the water at the bottom surface. Okay, so if you have a diver where he has a weight of 800 newtons and the upthrust on him is also 800 newtons, then he will remain at the same level because the forces are balanced. But if the weight is greater than the upthrust, then he will sink down. Okay, we can also you have to know that the upthrust is equal to the weight of fluid displaced. Okay, so let's say we have a Eureka can or a displacement can. Okay, I will draw that like that. That is the displacement can, and this is filled to the brim. Okay, to the spout rather. Okay, this is filled with water to the spout. Now what will happen is, if I add an object into this, okay, so let's say I put an object in here. Now as soon as I slowly immerse the object in here, what will happen? There will be a fluid displaced. Okay, so now in the beginning this was at this level. Okay, this was not inside, but as soon as I start slowly lowering this, what will happen is the water level will try to rise, but the water level can't rise up here, so it will go into this beaker. Okay, so what will happen is when this is fully immersed, all the water that rose up will go over here. Okay, so there will be some liquid here. Now the volume of this liquid is equal to the volume of the object. Okay, so we can say the volume of water in this beaker. Okay, in the beginning the beaker was empty. The volume of the liquid in the beaker, which is the volume that came out from this eureka can, also called displacement can. This is a spout, so that came out of the spout is equal to V volume of the object. The reason, because when you add this, so the rise in water level is equal to the volume of the object. Okay, you have already learned that. Okay, one way of measuring the shape of an irregular shaped object was to add the object into a measuring cylinder containing water. Okay, so I mean, you have learned this in the O-level classes. Okay, we have measuring cylinders of different sizes. Okay, and you have learned how to measure the volume of an irregular shaped object. Okay, now let's say we have this measuring cylinder, there is water in there, and slowly we immerse the irregular shaped object into this. Then what will happen? The liquid level will rise up. Let's say it's now the liquid level is at this level. Earlier it was at this level before adding the object. Now this rise in water level or rise in liquid level corresponds to the volume of this. Okay, so the final volume, the volume of this irregular shaped object will be equal to, now let's say the reading here is Vf and the reading here is Vi. Then the volume of the object will be Vf minus Vi, the increase in volume of the water once this is added. The rise in water level is equal to the volume of the object. Okay, so that is what we have here also. The water level tries to rise, but it can't rise because it was filled to the brim, so it gets collected here. So the volume of the liquid is equal to the volume of the object. And Archimedes' principle states that the weight of the liquid displaced is equal to the upthrust. Okay, so if you calculate the weight of this liquid, the weight of the liquid is equal to the upthrust on this object here. Okay, so if a greater volume of water is displaced, there will be a greater weight here, so the upthrust will be more. Okay, so the greater the volume of water or liquid displaced, greater the upthrust, because the greater the weight of the liquid that collects here. Okay, so you have to remember all this, very important. Now let's see. Okay, so what happens is, now let's say there was a brick which went into the water and then it came to the bottom here. Now when it is at the bottom, it is in equilibrium. Okay, it's not moving anywhere, so it's stationary. That means it's in equilibrium. Then we can say the total upward forces is equal to the total downward forces. So what we can say here is U plus R is equal to W. The weight of the object is equal in magnitude to the sum of R, the reaction force or normal contact force, plus the upthrust. Okay. Okay, so there are some calculations here. Why does a brick sink? And you can also calculate the value of the upthrust. Now, like I said before, the upthrust is equal to the weight of fluid displaced, and they are calculating the upthrust. Okay, so you know the volume of the liquid displaced is the density times the mass. We have the equation density is equal to mass over volume. Okay, I will write that here. Okay, we have density equals mass over volume, and then the mass is equal to density times volume. Okay, and that's what they have used here. they know the density of water. Now what happens is when the brick, in this case, in this example, there's a brick in the water. Okay, you can see the brick in the water. So they are calculating this U, upthrust. So the first thing is we can find the mass of the water that was displaced. Okay, the volume of water displaced is the volume of the brick, which is this value, and the density of water is 1000 kilograms per cubic meter. So we are using this equation to find the mass of the water displaced, and then when you times it by 9.81, the gravitational field strength, you get the weight of water displaced, and the weight of water displaced is equal to the upthrust, which is 15.8 newtons in this example. So there is an upward force on the brick of 15.8 newtons. This is what we call the upthrust. Upthrust is equal to the weight of fluid displaced, and this is the mass of fluid displaced. The volume of the liquid displaced is the same as the volume of the brick. Right, so we get this, and Archimedes' principle states that the upthrust is equal to the weight of fluid displaced. Now this W here is the weight of the brick. The weight of the brick is the mass of the brick times the gravitational field strength. So you get this one, the weight of the brick. Then the upthrust is what we calculated here, which is 15.8. And you can see the upthrust is less than the weight. This force here is less than the weight force here. So what will happen is the brick will sink. So the brick will accelerate downwards. Now this is the resultant force. When you subtract, the difference between these two forces is 17.6 newtons. So it will accelerate downwards because there is a resultant force until it reaches the bottom of the pond, which then exerts an extra force up to balance the weight. So the brick rests stationary on the bottom with zero resultant. Okay, so that's what happens here. So it comes all the way to the bottom. Now the resultant force is equal in size to this one. The resultant force was downwards before, but once it hit the ground, there is a normal contact force exerted the other way, which is equal in magnitude to the resultant that was here. Okay, so 17.6 newton downwards was the resultant force. The normal contact force here is also 17.6 newtons. So there is no net force or no resultant force when the brick is at the bottom of the pond. Okay, so it will be in equilibrium. The resultant force is zero, therefore it will be stationary. And here is another example. A giant garbage bag on New York's Hudson River is 60 meters long and 10 meters wide. What depth of the hull will be underwater if it and its cargo have a combined mass of 1500 tons? Assume that the density of water in the Hudson River is 1000 kilograms per cubic meter. Now this is the typical density of water, 1000 kilograms per cubic meter. Now if it is to float, the upthrust should be equal to the weight. If the upthrust is greater than the weight, the object will rise up. Okay, for example, let's say you have an inflated balloon which you release underwater. If you release an inflated balloon underwater, you tie the balloon so that no air comes out. Okay, you have a tied balloon full of air which you take underwater and you release it. What will happen then? The balloon will rise to the surface of the water. Because the upthrust is greater than the weight, it will come all the way to the surface of the water until it displaces water which has a weight equal to its weight. Okay, so what happens? We'll draw a diagram and show it to you. Okay, so let's say you release a balloon underwater. Now this is how we can understand why some objects float higher and some objects float lower. Okay, so let's say you release a balloon. The balloon was here, the tied balloon. Okay, and then you release it. What will happen is the balloon will now rise all the way to the top because the upthrust is greater than the weight. So eventually the balloon will be somewhere here. Okay, part of the balloon is underwater, but you might notice the majority of it would be above water. Now you can see here only a small volume of water is displaced. The volume of water displaced is equal to the volume of the balloon underwater. The volume of the balloon underwater is equal to the volume of the water that it displaces. And since it's a very small volume of water that is displaced, the upthrust is very small. Okay, so what happens is when it was underwater, a huge volume of water was displaced, so the upthrust was greater than the weight. Now it will come all the way up here until it displaces a small amount of water, where the weight of the water is equal to the weight of the balloon. So when the weight of the water that it displaced is equal to the weight of it, that is the balloon, then the forces are balanced. Okay, so now we have the weight force downwards, and then we have the upthrust upwards. Both forces are equal in magnitude and opposite in direction, so the balloon will float, or it will remain at that level. It won't sink or it won't rise up further because the forces are balanced. Okay, then so let's go through this. Okay, so they are asking about this, you can say about the ship. Okay, so garbage barge, 10 meters wide, 60 meters long. What depth of the hull will be underwater if it is cargo combined mass? Okay, so the total mass is given, which is 1500 tons, and in 1 ton you have 1000 kilograms. So this will be 1.5 million kilograms. Okay, so they are already converting it to kilograms here. This will be the weight of the barge, okay, or the ship, you can say. So this will be, okay, so this is the mass of that, and then in kilograms times 9.81, you will get the weight of it. Then upthrust should be equal to the weight if it is to be remaining stationary. Okay, so we said that we take that value to be equal to the upthrust because it has to float. Okay, so if it is to float, then these two should be equal. The upthrust is equal to the weight of volume of water displaced by the hull. Upthrust is equal to the weight of water. Now this is again Archimedes principle. Upthrust is equal to the weight of fluid displaced, and what it displaces in this example is water. So the upthrust is equal to the weight of the volume of water displaced by this hull, by the barge, and that is again upthrust is equal to the weight of the liquid now that was displaced. So the weight of the liquid is this. Okay, so this part is the mass. Okay, it's density times volume, which is the mass. So the density times the volume, that will be the mass. Okay, so this we get from the formula, density equals mass over volume. So the mass of the water displaced times the gravitational field strength will give you the weight of the water displaced. This side, on the right side, this is the weight of water displaced. On the left side, it is the upthrust. And since Archimedes principle states that the upthrust is equal to the weight of water displaced, we can set these two equal to each other. Then we get volume of the hull. Now we can assume it's rectangular in shape, okay, something like the brick shape. So we have length of hull, width of hull, depth of hull, and that will give us the volume of the hull. You can assume that it is a rectangular block shape. Okay, so we know the upthrust, and that is this much, okay, which we calculated. The upthrust is equal to the weight of fluid displaced, and that is the, okay, using this formula, right, density of water times the volume of the hull times width, sorry, the 60, yeah, the volume. So 60, okay, so it's what, length into width into depth. So that is what we have here. This is the volume. Okay, so we are using this formula. Rho is the density of water. This is the volume of water displaced, which is the volume of the hull underwater. Okay, this one. So that will be the length into the, see, it's 60 meters long, 10 meters wide. So length into width into the depth below the water. This is the depth of the hull below the water, and that will give you the volume of the hull underwater. So we are using the formula, this formula, okay, length into breadth into height, or length into width of the hull into the depth of the hull underwater, because that is the volume of water displaced. We assume this hull is rectangular in shape, like the shape of a brick, rectangular block. Okay, so then this will be the volume, this will be the density of water, and then we times it by 9.81, we get the weight of water displaced by the hull. This is the weight of water displaced by the hull, and it is equal to the upthrust. Okay, now we already found what the upthrust is, which is this one. So on the left side we can write that value. Okay, so this value 1.47 into 10 to the power 7 can be written here. Then we make d the subject of the equation, so it will be this divided by this. Then you will get 2.5 meters. The hull will be 2.5 meters under water. Any questions?
No, sir.
Okay. Then we have an instrument called the hydrometer. The hydrometer can be used to measure density. Okay, density of liquids. A hydrometer floats lower density, more alcoholic red wine than white wine. Okay, now if the density is more of the liquid, the upthrust will be less on the object. You can imagine something like water. Okay, you have water and a wooden block. Now wood is less dense than water, so wood will float on water. Now let's say we have this. Okay, so this is water, and then we add a wooden block onto the water. Let me see whether I can use a different color actually. Okay, so let's see, I think I have the, okay, it's here. Alright, so let's say I use I have a wooden block. So the wooden block will be under the water. Okay, so what happens is, now if you add salt, more and more salt to this water, what happens it increases the density of water. Salt water is more dense than fresh water. So if I add salt to this water, what will happen is the density of this water will increase. And when the density of the water increases, the upthrust will decrease. Okay, so this will rise higher because it has to float. So then what will happen is this will be higher up. Okay, so instead of being here, the wooden block will be floating much higher up. So that means less water is displaced. And if less water is displaced, so if now let's say this is the new position, let's say somewhere there. Okay, now let's say it rose up a bit. Now this will be the new position. Okay, so you can see the portion of the wooden block under the water is less now. Therefore the upthrust will be less because less fluid is displaced. Okay, so when you add salt to the water, the density of water increases, and that reduces the upthrust. So the object will float higher up, so that the upthrust is equal to the weight. A good example is of the Dead Sea. If you have been to the Dead Sea, you will notice that people float much higher up compared to in fresh water, because the Dead Sea has a high salt concentration. So it has a much higher density, and the density of the human body is almost equal to the density of water, but a bit lower. That's why humans normally float on water than sink down. So because the density of the human body is almost same but a little less, so that people float very close to the surface of the water. Now what happens in salt water is the density is higher. So if you see in the Dead Sea, the people float much higher than in normal water. Okay, so this we need to understand this to understand the hydrometer. Now, like I said, the denser a liquid is, the lesser the upthrust, so the more higher the object will float. Same thing applies to this hydrometer. You can see this part here. Now the hydrometer is inside a measuring cylinder. This whole thing is not the hydrometer, it's just this part. Can you see something vertical inside that? That is the hydrometer. This thing. So here it's inside this also. Okay, the hydrometer is such that you can see the mass of the hydrometer is concentrated here. You can see the center of mass. So it is made such that it will always be vertical when you add it into a liquid. But it will float higher up when the density of the liquid is more. Okay, now the reason why is like this, what I told you about the wooden block. I told you when the density increases, the object will float higher up because the upthrust will decrease. Okay, so that now if something is to float, the weight should be equal to the upthrust. So when you make the density of the liquid greater and greater, the upthrust will be lesser, so it will have to be much higher up so that it displaces less fluid, so that the weight will equal the upthrust. Okay, again we can also write it in terms of the equation. Now we know upthrust is equal to the weight of fluid displaced. The weight of fluid displaced is the mass times g, and that is what density times volume is mass times g. Okay, so if you increase, now to get the same upthrust, okay, let's say this is constant, to get the same upthrust, the g is a constant. Okay, so when the volume when the density increases, the volume should decrease to get the same amount of upthrust. Okay, so I think I said upthrust decreases, but what happens is actually it's constant. Okay, not decrease, the upthrust is constant, but when you increase the density, you can get the same upthrust with a lesser volume. Okay, so that's what really happens. But also you can see, I mean, when it is deep, much deeper inside, it displaces a greater volume of fluid. Okay, so here what happens is the upthrust is the same. The upthrust doesn't change when you increase or decrease the density. Upthrust is the same, but when you increase the density, you need a lesser volume to produce the same upthrust on the object, because you see the weight of the object is the same. The weight of the object, it is constant. The weight of the object is not changing, but the what happens is the volume of liquid changes. So you will need a greater volume of liquid to produce the same upthrust, because the total upward force should equal the total downward force for this to be balanced. So always the upthrust should equal weight, and when you add when you make the density higher, you can get the same upthrust with a lesser volume of liquid. Okay, so actually the upthrust is not changing, it's still the same, but this displaces less fluid. Okay, but we are changing the density, that's why. Alright, so the hydrometer, you can see hydrometer sinks more in less dense material, and there is a scale on the hydrometer. You can see here there are markings on the hydrometer which indicate what the density of the liquid is. So the reading here at the meniscus of the liquid where the hydrometer is, the reading that you see on the hydrometer at the meniscus of the liquid is the density of the liquid. Okay, so if you put this in a denser liquid, it will be much higher, which means the hydrometer reading will give a higher value. If it is in a less dense liquid, the hydrometer will sink much more down, so and it will give a lower reading. Okay, so always the hydrometer will be vertical, because the way it is made, the center of mass low means stability high, so it will be vertical always. A hydrometer floats lower in lower dense, more alcoholic red wine than in white wine. Okay, now we'll see some examples. You can see the densities. Alcohol by volume given as the percentage proportion of alcohol. Okay, so you see, comparing the density of alcoholic drinks with that of water gives an indication of the proportion of alcohol they contain. The lower the density, the greater the alcohol content. As alcohol has a lower density than water it is mixed with. So if you
if the density is lower, sir, it floats more up. No, sorry, if the density is higher, it floats more up.
Yes, correct. Okay, the lower the density, the greater the alcohol content. As alcohol has a lower density than the water it is mixed with. So if you have alcohol and water, and if you mix the two together, the more the percentage of alcohol in the solution or the mixture, the greater the lesser the density, because alcohol is less dense than water. This has long been the basis for the taxation of alcohol. So they use that to tags. For example, you can see this table. Okay, so it's just still sparkling cinder and peri still. Okay, so we have some examples, and where you can see the alcohol content. When it increases, the taxation rate increases. Okay, so wine, sparkling wine, handmade wine. Can you see when the alcohol percentage increases, the taxation rate increases? Okay, so we have come to the end of that. Now these definitions are very important. You should know them. Fluid is defined as any substance that can flow. Density is a measure of the mass per unit volume of a substance. You know the formula, density equals mass over volume. And upthrust is an upward force on an object caused by the object displacing fluid. Again, very important. Upthrust is equal to the weight of fluid displaced. Archimedes' principle states that the upthrust on an object is equal to the weight of fluid displaced. Hydrometer is an instrument used to determine the density of a fluid. Okay, then the next topic is fluid movement. Fluid movement. By this section, you should be able to understand the terms laminar flow and turbulent flow. Laminar flow is also called streamline flow. You have to know the two different terms. Laminar flow is called streamline flow, and the other one is turbulent flow. Okay, we will when you see some pictures, I think you will be able to understand it. Okay, so here we have laminar flow. Can you see these lines are called streamlines? Okay, here also they have shown them. Okay, so by lines they indicate the direction of flow of the fluid around the object. When a fluid moves, there are two ways this can happen. That is laminar flow, also called streamline flow, and turbulent flow. Now, if you understand that when the speed increases, the flow changes from laminar to turbulent. Okay, the flow which produces more friction is the turbulent flow than the laminar flow. So what we want to do is minimize turbulent flow and increase the laminar flow. If an object is streamlined, then it will have laminar flow until it reaches a very high speed. Okay, compared to an object which is not streamlined. In an object which is not streamlined, the turbulent flow will come at a lower speed. Okay, so laminar flow and turbulent flow. Laminar flow produces less friction compared to turbulent flow, and an object moving in a fluid can have more laminar flow or prominent laminar flow above a certain speed. Okay, so laminar flow occurs at lower speed and will change to turbulent flow as the fluid velocity increases past a certain value. So it's very important. The velocity at which this changeover occurs will vary depending upon the fluid in question and the shape of the area through which it is flowing. So if you have something like very sharp shape, that is like a streamline shape, also we call aerodynamic shape, then the friction will be less because this will have laminar flow instead of turbulent flow. Now you can see this person, the skier, is shaping himself into a streamline shape by bending like this, by wearing these clothes. So that way he can increase his speed because the air resistance will be less. So here he has laminar flow. Now if he stands up, if he stays kind of like flat instead of curling like this, if he stays flat, what will happen is there will be turbulent flow. The airflow won't be smooth around his body. It will go here and there. That is what we call turbulent. Now from the name itself you can try to understand turbulence. Okay, so turbulent flow. Laminar, also called streamline. You see, laminar flow is called streamline. Can you see? It's a streamline shape. And then turbulence, you can remember, turbulent flow, where the streamlines are here and there and they cross. We will learn about streamlines also. Okay, so each of these lines we can consider to be a streamline. Okay, so in laminar flow, these streamlines don't cross. In the exam papers, I have seen they had asked students to draw the streamlines. Okay, so if you want to indicate streamline flow with streamlines or these lines, make sure they don't intersect. because in streamline flow they don't intersect, but in turbulent flow they do intersect. Okay. So if you draw these same lines for turbulent flow, you have to draw them curling. Okay, they are what we call eddies or vortices. Okay, where you draw them like circles, and then they also have to intersect. Now you can see this diagram. Okay, so there, here we will have some turbulent flow. Okay, where they intersect. Here we can have laminar flow. Where the streamlines are parallel or not intersecting is where we have streamline flow. Now you can see here also, can you see the smoke trails? This is done inside what we call an air tunnel. Okay, this is to check the design of the car so that it is very aerodynamic, highly streamlined or highly aerodynamic, and that minimizes the turbulent flow. When you minimize the turbulent flow, or when we have turbulent flow occurring at a very high speed, then the car uses less fuel. The car uses less petrol or diesel. Okay, because it has to do less work against air resistance. Okay, so what happens is they are sending this air and then finding at which speed it changes from streamline flow to turbulent flow. If they can achieve that change in streamline flow to turbulent flow at a higher speed, then this car will use less fuel, less petrol, less diesel, less gas. Okay, and that's what they are checking. And also we can say it can go faster. Okay, so for the same amount of power it can go faster because it has to do less work against air resistance when it has a very good streamline shape. Okay, so these are smoke streamlines, show laminar flow of air over a well designed car. And then we'll talk about turbulent flow now. The flow becomes chaotic. Okay, so in turbulent flow the fluid velocity in any given place changes over time. So here you can see it's all going almost like parallel, okay, not intersecting. But if you consider turbulent flow, it's everywhere, like, you know, no order like this. It's intersecting, the streamlines intersect, and also it goes in curls, whirls. We will see that. In turbulent flow, the fluid velocity in any given place changes over time. And also these streamlines, what we can see is, now this is actually in a pipe. Okay, so the water in the pipe in the middle is traveling the fastest because less friction over here compared to where the water is close to the surfaces of the pipe. Okay, so now you can see this is the middle of the pipe. Here we have the surfaces of the pipe. When it's close to the surface of the pipe, the friction is more. Why? Because the water is rubbing against the surface of the pipe. So here you can see this is slower. The water here is slower than the water here. The water here, in other words, is faster than the water here because less friction from the surface of the pipe. Okay, so here we will have the maximum speed of the water compared to, and here at the surfaces we will have the water flowing the slowest. Okay, let's go back. Okay, so here what do we get? Streamline flow. Here we have turbulent flow. When the speed increases, we get turbulent flow. You can see the water here is at a very high, moving at a very high speed. Now let's say you go on top of a bridge or on top of a dam, and if you notice that in this water you may be able to swim, but if you try to swim in this water you won't be able to do it because it's here we have turbulent flow. The water is flowing very fast. Okay, so here the water looks calm. So here we have streamline flow, here we have turbulent flow. Streamline flow is when the speed is low. Turbulent flow is when the speed is high. In turbulent flow, the fluid velocity in any given place changes over time, and you can see the velocity here may be different from the velocity of water here, but here we can say it's almost the same. The flow becomes chaotic and swirling eddies form. You see eddies when the water runs away through a plug hole. A poorly designed car would cause turbulent flow of air over it. In the wind tunnel, the smoke trails over the car would be seen to swirl in ever-changing patterns. Now that is if there was turbulent flow. So maybe somewhere at the back there would be turbulent flow. Turbulent flow increases the drag on a vehicle and so increases fuel consumption. Okay, So that is about laminar flow and turbulent flow. Okay, you have to know these definitions. Laminar flow is also called streamline flow, is where a fluid moves with uniform lines in which the velocity is constant over time. Okay, so velocity is constant over time. Along a streamline, the velocity is constant. Now if you consider this streamline, along this streamline the velocity is constant. Then if you consider another streamline, along that streamline the velocity is constant. Turbulent flow, okay, is where the uniform in which the velocity is constant over time. Uniform lines. Turbulent flow is where fluid velocity in a particular place changes over time, often in an unpredictable manner. Streamlines are lines of laminar flow, you see that, in which the velocity is constant over time. So actually this word streamline is used for laminar flow, and when it comes to turbulent flow we use these words. You can see here swirling eddies, we also call them vortices. The flow becomes chaotic. Okay, so remember the streamlines are lines of laminar flow in which the velocity is constant over time. Okay, then the next one is about the drag act. Drag act. Now drag is what? A frictional force. Okay, that is due to a fluid. If an object is moving in a forward direction, the air resistance or drag act, or it can also be due to a liquid. Okay, so that is in the opposite direction. Always friction opposes the motion. Okay, and this swimmer has a specially designed suit which minimizes the friction due to water. Okay, the shark skin suit helped break many swimming world records at the Beijing Olympics. It was later banned by swimming governing bodies as technology doping, despite the manufacturer's claim that this was due to the material's extremely low viscous drag. Okay, so we call that drag actually the drag due to the air resistance if it's in air, or water resistance, that is if it was in water we call that drag. Okay, also viscous drag. Okay, then scientists discovered this to be false and put the success down to its psychological benefit for athletes. Okay, so this minimizes the friction, this suit, so that the swimmers can swim faster. Okay, now how this drag arises is due to something called viscosity. When you wade through a swimming pool, you will find it is much harder than walking through air. The friction acting against you is greater in water than it is in air. This frictional force in fluids is due to viscosity. Okay, you see this frictional force in fluids is due to viscosity. Now a material or a liquid that flows faster has a lower viscosity. So if something is more viscous, if the viscosity is high, also we can say if the coefficient of viscosity in a certain liquid is higher, then that liquid flows at a slower rate. For example, if you consider water and let's say ketchup, okay, ketchup. Now water flows faster than ketchup, therefore water has a lower coefficient of viscosity than ketchup. Okay, so the ketchup is having a higher viscosity, it has a higher coefficient of viscosity, and also we can say if the coefficient of viscosity is high, then the viscosity will also be high, so it flows slower. Okay, so the frictional force in fluids is due to viscosity. If the frictional force caused by movement through the fluid is small, we say the viscosity is low. Then Newton developed a formula for the friction in liquids that included several factors. One of these factors relate to the particular liquid in question. Clearly, it would be even harder to wade through a swimming pool of trickle than one full of water. Okay, so if a swimmer tries to swim through, maybe instead of water, oil, his speed will be lower because the viscosity of oil is higher than that of water. Okay, the fluid dependent factor is called the coefficient of viscosity and has the symbol eta, the Greek letter eta or eta or eta. Okay, then so this is the symbol we use for coefficient of viscosity. Okay, as viscosity determines the friction force acting within a fluid, it has a direct effect on the rate of flow of the fluid. Consider the different rates of flow of a river of lava. Table A river of water 1 meter per second and natural gas flowing through a pipeline 3.5 meters per second. Okay, let's have a look at table A. Okay, you can see that lava, so this is for lava, and water, it flows 1 meter per second, and natural gas flows even faster, flowing through a pipeline. Okay, there was a question in a past paper regarding these lava types. You can see lava, this one, silica content least, viscosity least. Then the flow rate, what I told you is when the viscosity increases, the flow rate decreases. Okay, so yes, so when the viscosity increases, the flow rate decreases. For example, ketchup has a high viscosity. It has a high viscosity because it has a high coefficient of viscosity. So it flows slower. Okay, so this one, basaltic least viscosity 30 to 60 kilometers per hour is the flow rate. Okay, very least silica content least, viscosity least. And then if you look at the last one, rhyolitic, most silica content, then most viscous, and therefore the flow rate is least out of those three. How is the rate of flow related to viscosity of the fluid? Now you know already, when the viscosity increases, rate of flow decreases. And the rate of flow of a fluid through a pipeline is inversely proportional to the viscosity of the fluid. And here is an investigation, and then they are proving connection between flow rate and viscosity. And this person was interested in blood flow through the body, but his law is immensely important in industrial design. For example, the rate of flow of liquid chocolate through pipes in the manufacture of sweets will vary with the chocolate's viscosity, which will vary depending on the exact recipe to produce it. More sugar may mean greater viscosity and thus lower flow through the pipes, and so less chocolate per sweet. Okay, so here is an investigation, you can go through it. So constant pressure water forced through a narrow pipe. Okay, so here we have this. Narrow pipe will flow at a certain rate, inversely proportional to its viscosity. By varying the height of the water tank, you can record measurements of this head of pressure H against the flow rate. The gradient of the best fit line will allow you to calculate the viscosity of the water. Okay, so we have a graph, record measurements of H against the flow rate. Okay, so you can go through that one. Then that one you can, I think, calculate the viscosity. Yeah. Okay, you can go through that. Then okay, now there is a difference for gases. Okay, for liquids we learned that when the temperature increases, the viscosity decreases. You don't even need to think. Now let's say you have ketchup. Ketchup, you put it in the freezer and take it out. Not in the freezer, maybe in the refrigerator. Okay, where it's very cool. You put it inside and take it out and try to pour it. What will happen? It will not pour or flow out fast. Whereas if you keep it outside, maybe at 30 degrees Celsius, you keep it under the sun, then the ketchup flows faster. So when the temperature increases, the viscosity decreases. Okay, you can see that here. If you consider water, this is for liquids. Okay, now you can see water 0, 20, 100 degrees Celsius. That is the temperature. See, when the temperature increases, you can see the viscosity decreases. You see that? Because it flows faster. If you increase the temperature, water can flow faster. So that means flowing faster means viscosity will be less. When the temperature increases, the viscosity decreases for liquids. And you can also see that here, look at this one, chocolate at 30 degrees Celsius and at 50 degrees Celsius. When the temperature increases, the viscosity decreases, so it flows faster. And yeah, even this also you can see when the temperature increases from -40 to 30, again the viscosity decreases, meaning it flows faster, it can flow faster. But if you look at the first one, that is air is a gas. So in gases this is the opposite. Okay, in gases, when the temperature increases, the viscosity also increases. You have to remember all these things. In gases, when the temperature increases, the viscosity also increases, so it flows at a lower rate. Okay, now here is an experiment to check the viscosity. How we do this? We fill this can halfway. Okay, fill it like you can investigate how the viscosity of a liquid changes with temperature using a resealable tin or bottle half full of a test liquid such as golden syrup. The temperature of the liquid is varied until using a water bath. The viscosity of the liquid will affect the rate at which the tin or boil rolls down a fixed ramp.
So in gases, even increases, sir.
What happens is, now you fill this halfway. Okay, now if this was at a higher temperature, the liquid flows faster. So what will happen is this will roll down faster. It will take a shorter time to go from here to here. If the substance in this, if the liquid in this is at a higher temperature, it will flow faster. If the liquid in this is at a lower temperature, then the viscosity will be high, meaning the flow rate will be low, so it will take a longer time for this cylinder to roll down here. So when the temperature is low, it will take a longer time. When the temperature is high, it will take a shorter time, because when the temperature increases, the viscosity decreases. Okay, so they are asking how the viscosity of golden syrup changes with temperature, and I already told you. Okay, so you can answer all these questions.
I'm asking, so why does with temperature the viscosity of gas increases?
Okay, so that's another thing. Okay, so what you need to remember is this. Okay, maybe after the lesson we can discuss that, but this is the most important part. Okay, so that's another topic. All right, so you can answer these questions. Then the definitions are important. Viscosity is essentially the idea of how resistant a fluid is to flowing, although a complete definition is beyond the scope of this book. So like what I said, okay, so if you go into detail, it's out of the syllabus, so you can remember this. Okay, viscosity is essentially the idea of how resistant a fluid is to flowing. Then we have coefficient of viscosity is a numerical value given to a fluid to indicate how much it resists flow. Okay, so this coefficient of viscosity, it has a value, but viscosity is a slightly different. Okay, it is the idea of how resistant a fluid is to flowing. So viscosity has a numerical value, but this doesn't. Coefficient of viscosity has a numerical value, but not the viscosity. But what you have to understand is, higher the coefficient of viscosity, higher the viscosity, slower the fluid will flow. And when the temperature increases, the viscosity decreases for liquids, but for gases, when the temperature increases, the viscosity increases, so the flow rate will be low. All right, then the next topic is terminal velocity. Now terminal velocity, this applies for something.
I'm okay with terminal velocity. Can we start Hooke's law, sir?
Okay. Let me